What is up, guys? This is Physics 2211 Lab 5. Choose your own adventure. Starting it off with a table of contents, we're going to be going over an introduction, motion of a falling slinky, analysis of results, and discussion. So, going over some key concepts, first is Newton's second law of motion, which states that force is equal to the rate of change of momentum, which we can see net force is equal to change in momentum over change in time. And we're going to be using the velocity update formula and position update formula to predict some motion. Next, we have the gravitational force, which is gmm over r squared. And we know that near Earth's surface, we say weight is equal to mg, g being about negative 9.8 meters per second squared, and drag force, which acts in the opposite direction, as mg. Next, the spring force is going to be very important in our upcoming calculations, and the experiment is going to measure the motion of a stretched slinky falling from rest near Earth's surface. Our system is the slinky, surroundings being the ground, and some initial conditions. So let's take a look on tracker at the video. He is holding this slinky from one end. The slinky is at rest, and we'll see what happens when he lets go. So as you can see, right when he lets go, if we take a look at the bottom of the slinky, it stays exactly in place even though the top is falling. And once the top hits it, it starts falling to the ground. So we know that there's some kind of force, if we look at the bottom of the slinky, that holds it in place, because mg is pulling it down. So in order for it to stay in place, there's a force acting up on it. And in order to show this better, if we take a look at predicting observed motion using glow scripts, I have a script that also shows something similar. This is a slinky, and as we run this program, we also see as it lets go, the ball starts falling, but the bottom of the slinky does something similar where it stays in place until it gets to a certain point. And what does it mean? Why does the bottom of the slinky stay stationary? Well, we know it's in static equilibrium because there are forces acting upon it and it's still staying in place. So those two forces are gravitational force pulling it downwards and the spring force from the rest of the slinky above that point. So in its initial condition, the stretched slinky exerts a spring force on itself on the bottom, and that happens to be the same magnitude as the gravitational force pulling it down, keeping it in static equilibrium. Thank you for listening.